Hello everyone, welcome to the video lecture series on circuit analysis. This is the 14th video lecture series. In the last session, we have seen how we can convert the Delta network to Wye network and Wye network to Delta network, and we have derived the very important formulas. Now let's see examples which is used either of the two conversion steps. So as you can see for this circuit, we have asked to determine the total current I naught in the circuit given below. So let's start with solution. As you can see here, so some part of the circuit elements, the resistors are connected in series and the others are not connected in series or nor in parallel. So as you can see here, R5 and R6, they are connected in series. Okay, as you can see here, R5 connected with R6. So let's say this their equivalent would be R equivalent 1, which is equals to R5 plus R6, which is equals to 20 ohm plus 50 ohm, which is equals to 70 ohm, 70, okay, 70 ohm. So using this, we can draw the circuit. We can draw the circuit as you can see here, okay. So for example, so the circuit reduce to, okay, as you can see here, you have the source voltage, which is 24 volt, okay. So we have this, which is so this one is R1 20 ohm. This one is R4, which is 60 ohm, and this is R3, which is 40 ohm, and this is R2, which is 10 ohm, okay, 10 ohm, and this is R equivalent to 1, which is 70 ohm, 70. So we can consider here a number of configuration for the circuit, okay. That means this network is considered to be the Wye network, and this network also considered to be the Delta network, and as well this network considered to be the Delta network. So, or we can use this also. We can use this this network can be also considered to be the star network or the Wye network. So we can use either of the four configuration. Okay. So let's say this is let's convert this Delta network into the equivalent Wye network. Okay. So this is R1. This one is R2. This one is R3. After the Delta network resistors is obtained, so the Delta network will be removed from the original network. Okay, so first we know that for conversion of the Wye network, I mean the Delta network into the Wye network, we have R1, which is equals to R2 times R3 over R1, I mean R2 plus R3 plus R equivalent to 1. Okay, so we have this 10 times 40 over the sum of the three resistors, which is 120 ohm. Okay, so we have 40 over 12 ohm, 40 over 12 ohm. Okay, and and the other one is, let's say this is ry1, this is ry2, and this one is ry3. Okay, so ry2, which is r3 times r equivalent to 1 over the sum of the three resistors, which is the same, 120 ohm. Okay, so we have 40 times 70 over 120 ohm, which is equals to 280 ohm over 12 ohm. Similarly, ry3, which is equals to r2 times r equivalent to 1 over 120 ohm. Okay, so which is 10 times 70 over 120, which is equals to 17 over 12. 17 over 12. Oh, 17 over 12. Okay, so using this value, the original delta network will be reduced, so the circuit of the network will be reduced again. So the circuit will be reduced to as shown below. So as you can see here, the delta network is removed. Okay, so from this network we can have the values. That means R1, it is in series with R1 in series with RY1. Okay, so I can write R equivalent to, which is equals to R1 plus RY1. Okay, RY1. So which is 20 plus 40 over 12, which is equals to 280 over 12 ohm. 280 over 12 ohm. And the other one is R4 in series with R4 is in series with RY2. So I can write R equivalent to, which is equals to R4 plus RY2, so which is 60 plus 280 over 12, so which is 1000 over 12 ohm. Okay, so using this value, we can reduce the network again. Then, so the network again reduced to as shown below. We have this network configuration. From this network, we can conclude that R equivalent to is in parallel with R equivalent 3. So from this, I can write R equivalent. Their equivalent is R equivalent 4, which is R equivalent 2 times R equivalent 3 over R equivalent 2 plus R equivalent 3. Okay, so R equivalent 4, which is equals to 280 over 12 times 1000 over 12 over, okay, 280 over 12 plus 1000 over 12. So from this, when you simplify, R equivalent 4, which is around approximately 80.229 ohm. Okay, 229 ohm. Then using this value, you can also reduce the network again. So finally, R equivalent, the final value or the final equivalent resistance for the given network is given by R equivalent 4 is in series with RY3. So R equivalent, which is equal to R equivalent 4 plus RY3. Okay, So 80.229 ohm plus 5.833 ohm. So finally, you would have the total resistance, which is 24.0606. So this is the equivalent resistance, Then finally, the circuit will be reduced to a simple circuit consisting of voltage source in series with is a single resistor. That means this is R equivalent, which is 26.06 ohm. So we have the total current, I note. So we can apply Ohm's law. Apply Ohm's. That means just I equals to 24 volts over R equivalent. So which is 24 volts over, so this is 24.06, which is 24.06 ohm. So we have around 1 ampere, which is approximately 1 ampere. So this is how we can determine the total current for the given circuit, okay? So we can apply the conversion of, for any complex network, we can apply the conversion of delta to Y or Y to delta conversion, so that we can have the values of the voltage across any element or the values of the current through any element. Okay. Let's have another example. Okay. That means find example 2. Find, okay, R equivalent, and I note in the circuit given below. Okay. So this is the network. So we are asked to determine the current I note and the equivalent resistance are equivalent. Okay, are equivalent. So using this, we can first we need to understand the connection scheme of the network. Which section of the network elements are, or the circuit elements are connected in series, and which section of the circuit elements are connected in parallel. Okay, so as you can see here, you can consider the circuit elements R3 and R4. They are connected at this point. Their terminals are connected at this point, and the other terminals of R3 and R4, they are connected at this point. So they are connected in parallel. Okay, and at the same time, R6 and R7, they are connected at this point, and this is the same potential, and the other terminals of R6 and R7 are connected at this point. So they are connected in parallel. So we can write using this as solution, okay, using R6 and R7 are in parallel. Okay, so let's say they're equivalent to be R equivalent 1, which is equals to R6 times R7 over R6 plus R7. Okay, so which is 20 times 80 over 20 plus 80, which is equals to 16 ohm. Okay, 16. So again, R3 and R4. R3 and R4 are in parallel. in parallel. Okay, so we can write R equivalent to, which is equals to R3 times R4 over R3 plus R4. So using this 6 times T1 over 6 plus T1. Okay, so using their product with the same, so you have 4 ohm. So this is R equivalent to. Then the circuit reduced to be the circuit reduced to the network, as you can see here, which is plus or minus 35 volt. So this is R2, which is, this one is R1, and this is 2.5 ohm, and this one is 15 ohm. Okay, and this is R equivalent to, and this is R equivalent to 1. Okay, then you have, so this is R5, which is 60 ohm, and R equivalent 2, it is 4 ohm, and R equivalent 1, it is 16 ohm. So as you can see from the configuration, R equivalent 1 and R equivalent 2 are connected in series. Okay, in series. So their equivalent will be R equivalent 3, which is R equivalent 1 plus R equivalent 2. So which is 16 ohm plus 4 ohm, which is equals to 20 ohm. Okay, so the circuit again reduced. Circuit reduced to, as the circuit shown below here, which is 35 volt. Okay, again you will have R1, which is 2.5 ohm, and here is R2, which is 1.5 ohm, and here is R equivalent 3, which is 20 ohm, and we have R5, which is 60 ohm. Okay, so we can have here from this network configuration, R2, R equivalent 3, and R5 are connected in parallel. Okay, because their one terminals of the network are connected at this point, and the other terminals are connected at the same point. So we can have 1 over R equivalent 4, which is equals to 1 over R equivalent 4, which is 1 over R2, okay, plus 1 over R equivalent 3, plus 1 over R5, okay, so which is 1 over 1.5 plus 1 over 20 plus 1 over 60, which is equals to 60 over 4 plus 3 plus 1. So you have 8 over 60. So from this R equivalent 4, which is equals to 60 over 8 ohm. 60 over 8 ohm, which is 7.5 ohm. 7.5 ohm. Okay. So the circuit finally reduced to the circuit reduced to a simple circuit, which is plus or minus, which is R1, and this one is R equivalent 4, okay, which is 7.5, and this one is R1, which is 2.50. Okay, so this is 35 volt. So R equivalent, totally R equivalent, which is equals to the stress computation of R1 in series with R equivalent 4. So you have R1 plus R equivalent 4, okay, 2.5 ohm plus 7.5 ohm, so which is totally 10 ohm. Then finally, the circuit will consist of two voltage source and a single resistor. Okay, so you have R equivalent, which is 10 ohm. So you have I naught, and this is 35 volt. So I naught given by 35 volt over R equivalent, which is 35 volt over 10 ohm, which is 3.5 ampere. Okay, so this is how we can solve any circuit. This is how we can solve any circuit by reducing technique. So we are asked to determine the equivalent resistance, which is 10 ohm, and the total current, which is I naught 3.5 ohm. So using this approach, we can solve any circuit, any electric circuit given easily by applying Delta Wye transformation if the network is not consisting of either in series nor in parallel connection. Okay, that's all for this session. Thank you very much.